Welcome back to MathDogs. If you're new to the channel, please comment, like, and subscribe. If you have any questions, please comment down below. Today's topic is an algebra review. We got 60 topics and 96 problems in 3 parts. This is part 3, topics 41 through 60. Remember, we believe math is better with your dog, so call your pups. Let's get started. Problem number 63 is simplifying radicals. It says the square root of 40. So it helps if you have your square numbers memorized. If you don't, we're going to list a couple. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 5 times 5 is 25, etc. And we want to break this square root up using the product property for square roots into 2 factors. In the first square root factor, we're going to put all the perfect squares that are factors. And in the second one, we're going to put everything else. And so I have to think about the factors of 40 looking at my square numbers. Are one of these square numbers a factor of 40? And the answer is yes. There's a perfect square factor of 4 times everything else would be 10. The square root of 4 is 2. All I can do is express the other, and so my answer would be 2 times the square root of 10. Problem number 64 is also simplifying radicals. It says the square root of 32x to the 5th y to the 6th z. So again, I'm going to use the product property for radicals, and I'm going to break it into perfect factors and non-perfect square factors. So perfect square factors here, everything else here. So if I think about my number 32, I know that there's a perfect square number 16 times 2. So 16 will go in the perfect square radical, 2 will be in the other. If I look at x to the 5th, any even power is a perfect square. So the largest even number before I get to 5 would be 4. So I would have x to the 4th in the perfect part, and I would have an x left over to get to 5. Now I'm going to look at the y to the 6th. Well, 6th is an even number, so y to the 6th is a perfect square factor. Then I'm going to look at z. Z, there's a hidden 1 right here. To the 1st, I can't even get to an even number, so that would be in the other radical. Now I can take the square root of the perfect radical. The square root of 16 is 4. The square root of x to the 4th, I take 4 and divide it by 2 or cut it in half, which would be x squared. And y to the 6th, again 6 divided by 2 or cut 6 in half, and I would get y to the 3rd. My other radical, all I can do is express it as 2xz. And so my answer would be 4x squared y to the 3rd times the square root of 2xz. Problem number 65 is again simplifying radicals. It says the cube root of 16a to the 4th, b to the 7th, c to the 3rd. So we're going to use the product property one more time, and we're going to put our perfect cube numbers in the first one times all of our others. If you have your perfect cube numbers memorized, it makes the problem easier. If not, we'll list some. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64, etc. So now I need to think about the number 16. Looking at my list of perfect cubes, is there a factor of 16 that's in my list? And the answer is yes, there's 8. So I will put 8 in the perfect cubes times 2 in the other. Now I'm going to look at a to the 4th. This time we're not going to look for even numbers, we're going to look for multiples of 3. 3, 6, 9, 12, etc. I need the largest multiple of 3 before I get to 4. That would be 3. So I would have a cubed in the perfect cube root and a in the other to get to 4. Now I'm going to look at the b factor. I have b to the 7th. What's the largest multiple of 3 before I get to 7? And that would be 6. So I would have b to the 6th in the perfect cube and b in the other. Now I'm going to look at c. Well, 3 is a multiple of 3, so c to the 3rd is perfect. Now I need to take the cube root of 8a cubed b to the 6th, c to the 3rd. So the cube root of 8 is 2. The cube root of a to the 3rd, 3 divided by 3 is 1, so that would be a. Now I'm going to look at b to the 6th. 6 divided by 3 is 2, so that would be b squared. And then I'll look at c. 3 divided by 3 is 1, so that would be c. My other, I just have to express as the cube root of 2ab. And so my answer would be 2ab squared c times the cube root of 2ab. Problem number 66 is radical and exponent forms. It says write in exponent form the square root of 5. So if I have the square root of 5 and I add in the hidden numbers, there's a 2 here and a 1 here. To write it in exponent form, I'm going to put the 1 in the numerator and the 2 in the denominator. Or what I say, raise the root. So that would be 5 to the 1/2 power. Problem number 67 is again radical and exponent forms. It says write in exponent form the cube root of x squared. So I have the cube root of x squared, and remember fractional exponents indicate roots. So 2 will go in the numerator, 3 will go in the denominator, or again, I want to raise the root. So I have x to the 2/3 power. Problem number 68 is radical and exponent forms. It says write in radical form m to the 1/3. So this time I'm going to take what's written in exponent form and write it in radical form. So if I think about raise the root, I'm going to raise m to the first power inside, and then the root would be 3. So I would get the cube root of m. Problem number 69 is radical and exponent forms. It says write in radical form n to the 4/5. So I have n to the 4/5 as a fractional exponent, and I want to write that with a radical. Again, I'm going to raise the root. So n to the 4th raised to the 4th, and the root would be 5. So my answer would be the 5th root of n to the 4th. Problem number 70 is adding and subtracting radicals. It says the square root of 27 plus the square root of 18 minus the square root of 12 plus the square root of 32. So first we're going to have to simplify all 4 of these radical terms, just like we did in previous problems. First we'll look at the square root of 27. We're going to use the product property and break that up into perfect square factors times other. There is a perfect square factor of 9 times 3. Now we'll look at the square root of 18 and we'll do the same thing. Perfect square factor times others. Again, there's a perfect square factor of 9. This time it's times 2. Minus, same thing with the square root of 12. Perfect square factor times others. We have a perfect square factor of 4 times the other would be 3. And last, we'll look at the square root of 32. Perfect square factor times other, that would be 16 times 2. Now we'll go ahead and simplify each of the perfect squares. The square root of 9 is 3 times the square root of 3. All I can do is express the square root. Plus, again, the square root of 9 is 3 times the square root of 2. Minus, the square root of 4 is 2 times the square root of 3. Plus, the square root of 16 is 4 times the square root of 2. Now we can go ahead and add and subtract. It's very similar to combining like terms. Just like we could only add variables with exponents that were the same, we can only add radicals that are the same. So I would have 3 times the square root of 3 minus 2 times the square root of 3, or 3 square roots of 3 minus 2 square roots of 3 would be 1 square root of 3. And I don't need to write the 1 in front. That's a hidden 1 in math. I also have 3 times the square root of 2 plus 4 times the square root of 2. Or we could say it 3 square roots of 2 plus 4 square roots of 2 would be 7 square roots of 2. And so my answer would be the square root of 3 plus 7 times the square root of 2. Problem number 71 is solving radical equations. It says the square root of x minus 3 equals 5. So first I have to make sure my radical is isolated or all by itself on one side of the equal sign, which it is. To undo the square root, we're going to square it. And since I squared the left side to keep the equation in balance, I also have to square the right side. Taking a square root and squaring are opposite operations, or as some people say, they cancel one another out. and that will leave me with x minus 3. On the right side, 5 squared is 25. And now I have a very basic equation. I will add 3 to both sides to solve. Negative 3 plus 3 is 0, 0 plus x is x, and 25 plus 3 is 28. When I have radical equations, I do have to check to make sure that it comes out true. So I'm going to put 28 back into the original problem where x is and see if I get a true statement. So 28 minus 3 is 25. The square root of 25 has to equal 5, and 5 equals 5. So that's true. So my answer would be x equals 28. Problem number 72 is also solving radical equations. It says the square root of 3x minus 2 equals x. So first I'm going to make sure that my radical is all by itself on one side of the equal sign, which it is. To undo the square root, I'm going to square it, and since I squared the left side, I also have to square the right side. So the square root and the square undo one another, giving me 3x minus 2. On the right side, when I square x, I get x squared. All I can do is express it. Since I have a squared, I know it's a quadratic. To solve a quadratic, I'll have to set one side equal to 0. I'm going to set the left side equal to 0 so that my leading x squared term remains positive. So I would subtract 3x and add 2 to both sides of the equation. 3x minus 3x is 0. Negative 2 plus 2 is 0. So my left side is 0. On the right side, x squared minus 3x plus 2, they're not like terms, so all I can do is express that trinomial. Now I will factor. So I will factor the trinomial into two binomials. X squared will break into x times x, and I will need two factors of 2 that add up to 3. That would be 2 and 1. Both signs in the binomials will be identical because it has to multiply to a positive, and they will both be negative signs. Now I'm going to set each factor. Case 1, what if x minus 2 were the 0? Then x would equal 2. Case 2, what if x minus 1 were the 0? Then x would equal 1. Remember, with radicals, I have to go back and check. So the square root of 3 times 2 minus 2 has to equal 2. So I substituted 2 for the x in the original equation. 3 times 2 is 6. 6 minus 2 is 4. Does the square root of 4 equal 2? And the answer is yes. So x equals 2 is definitely one of my answers. Now we'll check 1. The square root of 3 times 1 minus 2 has to equal 1. Again, I just substituted the 1 for the x in the original problem. 3 times 1 is 3. 3 minus 2 is 1. Does the square root of 1 equal 1? And the answer is yes. So x equals 1 is also an answer. So my two answers would be x equals 2 and x equals 1. Problem number 73 is the imaginary number. It says the square root of negative 5. So first let's define the imaginary number. The imaginary number is defined as the square root of negative 1. And therefore the other definition, I squared equals negative 1. So we're going to use the product property and we're going to break this into the square root of negative 1 times the square root of 5. The square root of negative 1 is the imaginary number I, and all I can do is express the square root of 5. So I would get I times the square root of 5. Problem number 74 is also the imaginary number. It says the square root of negative 12x cubed. So I see there's a negative sign underneath my square root. That indicates I'm going to have an imaginary number, so that would be the square root of negative 1. Times, just like I did before to simplify, I'm going to break it up into the square root of the perfect square factors and the others. So, if I look at the number 12, I know there's a perfect square factor of 4, and the other factor would be 3. If I look at x cubed, remember I need my largest even number before 3, that would be 2, which is x squared, and my other factors would be x. So remember, the square root of negative 1 is the imaginary number I, and the square root of 4x squared is 2x. So I would write that as 2 2xi, and all I can do is express the other, square root of 3x. And so my answer would be 2xi times the square root of 3x. Problem number 75 is complex numbers. It says find the conjugate of 6 plus 4i. So complex numbers are numbers that are written in the form a plus bi. A is a real number and bi is an imaginary product. And so it says to find the conjugate of this complex number. Well, the conjugate is its difference of squares partner. So if I have 6 plus 4i, its conjugate would be 6 minus 4i. Problem number 76 is also complex numbers. It says find the conjugate of 3 minus 5i. So the same type of problem as before, I have 3 minus 5i. The conjugate is its partner in the difference of squares factoring pattern. It's going to be the opposite sign of negative. It would be 3 plus 5i. Problem number 77 is adding complex numbers. It says 8 plus 6i plus 2 minus 3i. So again, we have addition or subtraction. It's going to deal with combining like terms. In this case, I can add together my number terms, 8 plus 2, and get 10, and my imaginary products, plus 6i minus 3i would be plus 3i. So the I acts as a like term. It makes that product a like, and so I can combine them. And so my answer would be 10 plus 3i. Problem number 78 is subtracting complex numbers. It says 2 minus I minus 4 plus 7i. So I have an additional step. I will have to distribute the negative sign to the second set of parentheses or find the opposite of the numbers in the second set of parentheses. So I would get 2 minus I. The opposite of positive 4 is negative 4, and the opposite of positive 7i is negative 7i. Now I can go ahead and combine those things that are alike. So I have the numbers 2 minus 4, which is negative 2. And I have my imaginary products. Negative I minus 7i is negative 8i. And so my answer is negative 2 minus 8i. Problem number 79 is multiplying complex numbers. It says 5 minus 2i times 3 plus 7i. So first we have to remember the definition from a couple problems ago that I squared equals negative 1. Since these are two binomials, we're going to use FOIL, first, outer, inner, last. So let's multiply. 5 times 3 is 15. 5 times 7i will be 35i. Negative 2i times 3 is negative 6i. And negative 2i times 7i is negative 14i squared. So here's where our definition comes into play. I squared is negative 1. So this would be negative 14 times negative 1, which would be positive 14. So I would have 15 plus 35i minus 6i plus 14. And now it's just like combining like terms. I have 15 plus 14, which is 29, and I have 35i minus 6i, which is plus 29i. And so my answer would be 29 plus 29i. Problem number 80 is dividing complex numbers. It says 4 minus 5i over 3 plus 2i. So the trick with dividing complex numbers is to remember there's no division. To divide complex numbers, we actually multiply by a form of 1 that's the complex conjugate of the denominator. So let's look at that. First, I'm going to put the top binomial and bottom binomial in parentheses to help focus us. And then I'm going to multiply by a form of 1, which will not change the value of the original problem. I need to multiply by the complex conjugate of 3 plus 2i. And from a couple problems ago, that would be 3 minus 2i. And I'm going to put that on the top as well so that it's 1. So now in the numerator, I have 2 binomials to multiply. And in the denominator, I have 2 binomials to multiply. So let's multiply using FOIL. 4 times 3 will be 12. 4 times negative 2i will be negative 8i. Negative 5i times 3 will be negative 15i. And negative 5i times negative 2i will be positive 10i squared. But remember, I squared is equal to negative 1. And so in the numerator, this would actually be 10 times negative 1, which would be negative 10. So my numerator would be 12 minus 8i minus 15i minus 10. Now in the denominator, I'm going to multiply 3 plus 2i and 3 minus 2i, again using FOIL. And since it's a complex conjugate, the middle term should subtract itself out to 0. So 3 times 3 is 9. 3 times negative 2i is negative 6i. 2i times 3 is positive 6i, so these will add to 0. And 2i minus 2i is negative 4i squared. But again, I squared is negative 1, so this negative 4 will be multiplied by negative 1, which will give me a positive 4. So let's combine like terms in the numerator and combine like terms in the denominator. So 12 minus 10 is 2. Negative 8i minus 15i is negative 23i. In the denominator, negative 6i plus 6i is 0, or as some people say, it cancels out. And I would have 9 plus 4, which is 13. And so my answer would be 2 minus 23i over 13. Problem number 81 is the quadratic equation. It says 2n squared plus 5n minus 8 equals 0. So, if a quadratic equation is not able to be factored and use the zero product property, we have to use a formula. The formula says that the variable will be equal to, in this case n, is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So where do the a, b's, and c's come from? Well, they're the coefficients in the original equation. A is 2, b is 5, and c is negative 8. So all we have to do is substitute and simplify. So our variable n that we're looking for will be equal to the opposite of b, which is 5, and I'm going to substitute in parentheses like I always do, plus or minus the square root of 5 squared minus 4, a is equal to 2 times c, which is equal to negative 8, and all of that will be over 2 times a is equal to 2. So now I just have to simplify. So n will be equal to, the opposite of 5 is negative 5, plus or minus the square root of 5 squared is 25, and negative 4 times 2 times negative 8 will be positive 64. And on the denominator, 2 times 2 is 4. So now I just have to add underneath the radical, n will be equal to negative 5 plus or minus the square root of 89 over 4. Problem number 82 is completing the square. It says x squared plus 8x plus blank. So in this problem we want to figure out what does this number have to be to make a perfect trinomial square. So to find the missing number, I'm going to take the middle term, which is 8, and I'm going to need half of that middle term. So half of 8 is 4, and then I'm going to square it. So 4 squared is 16. So I would get x squared plus 8x plus 16. So that's the missing number, and that makes a perfect trinomial square of x plus 4 squared. So my missing number is 16. Problem number 83 is to solve a quadratic by completing the square. It says x squared minus 14x plus 30 equals 5. So if I check, half of 14 is 7, and 7 squared is 49. So 30 does not make this side, the left side, a perfect trinomial square. So the first thing I'm going to have to do is subtract 30 from both sides so that I can introduce my new number on both sides, which will make the left side a perfect trinomial square. So I would have x squared minus 14x, 30 minus 30 is 0, plus I'm going to leave a blank because that's going to be the number that I want to put in to make a perfect trinomial square, equals 5 minus 30 is negative 25, and whatever I add to the left side, I also have to add to the right side. So now we're going to go through the process we just did. Half of 14 is 7. 7 squared is 49. So I'm going to add 49 to both sides. Now, x squared minus 14x plus 49 is a perfect trinomial square of x minus 7 squared. On the right side, negative 25 plus 49 is 24. Now I can solve using the square root property. I'm going to take the square root on both sides. If I take the square root on both sides, remember a square and a square root undo one another, and so I would get x minus 7 equals the square root of 24. If you remember, we would break this into perfect square factors of 4 times others, which would be 6, and I would get plus or minus 2 times the square root of 6. I need to have plus or minus because when I take the square root of 24, I get both the positive version and the negative version. And now it's very simple. All I have to do is add 7 to both sides to solve. 7 minus 7 is 0, or as some people say, it cancels out. 0 plus x is x, which I'm looking for. And 7 plus or minus 2 times the square root of 6 can only be expressed, they're not like terms, and so I would get x equals 7 plus or minus 2 times the square root of 6. Problem number 84 is equations of parabolas. It says write in standard form and find the vertex of f of x equals x squared minus 16x plus 28. So the standard form of a parabola is y equals x minus h squared plus k. And my vertex is hk, so I have to transform this function into this form. So first I'm going to replace f of x with y, so y equals x squared minus 16x plus 28. And then I'm going to have to complete the square like we did in the previous problems. 28 is not the perfect square number we need to make this a perfect trinomial square. So I'm going to subtract it from both sides. So y minus 28 plus my new number that I'm going to add to the right equals x squared minus 16x plus my new number. So half of 16 is 8. 8 squared is 64. And so now my right side is a perfect trinomial square. I'll also have to add 64 on the left side. Negative 28 plus 64, combining like terms, would be y plus 36 equals x squared minus 16x plus 64 is a perfect trinomial square of x minus 8 squared. Now to simply finish this off, I would subtract 36 from both sides, and so y equals x minus 8 squared minus 36. So my vertex would be hk, so here's h, here is k. So my vertex would be 8, negative 36. Problem number 85 is graphing parabolas. It says y equals x squared minus 8x plus 7. So to graph a parabola, I need to know two things, a vertex and any other point, usually the y-intercept since it's pretty easy to find. So I'm going to use a shortcut, negative b over 2a. That will give me the x-coordinate of the vertex. A is the coefficient on the squared term, and b is the coefficient on the x term. So I'm going to have the opposite of negative 8 divided by 2, remember there's a hidden 1 right here, times 1. So dash dash means plus, so I would have 8 over 2, which would equal 4. So that's the x-coordinate of my vertex. Now I just have to find its y-buddy. So to find its y-buddy, I'm going to substitute 4 back into the original equation and solve for y. So y would be equal to 4 squared minus 8 times 4 plus 7. So y would be equal to 16 minus 32 plus 7. And when I add those together, y is equal to negative 9. So my vertex would be at 4, negative 9. Now I just need to find another point. Well, the easiest way to find another point is to find the y-intercept. I'm going to make x equal to 0. So y would equal 0 squared minus 8 times 0 plus 7. So y would equal 0 squared is 0, negative 8 times 0 is 0, plus 7. So my y-intercept would be 7. Now that I have those 2 points, I can do a rough sketch on the coordinate plane. My vertex would be at 4, 1, 2, 3, 4, negative 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. I know that's guaranteed to be a point, and my y-intercept is at 7, 1, 2, 3, 4, 5, 6, 7. So it also has to cross through that point. And so my parabola sketch would look roughly like that. Problem number 86 is transformation of functions. It says graph y equals x squared plus 2. So in transformation of functions, we have basic functions. In this case, it would be y equals x squared, and the plus 2 is the transformation. Since the plus 2 is outside of parentheses, it's going to be a vertical shift. So y equals x squared has a vertex at 0, 0, and it opens upward. If now I'm adding 2 to that, I'm going to shift this parabola up 2. So instead of the vertex being at 0, 0, it will be at 0, 2. And so my parabola would look like this. Problem number 87 is also transformation of functions. It says graph y equals the quantity x plus 2 squared. So again, I have the basic graph of y equals x squared. Remember, there's a vertex at 0, 0, and it opens upward. However, this time, the 2 is inside parentheses. That indicates a horizontal shift, and you do the opposite of what you see. So since it's a plus 2, I'm going to transform this left 2. So here's my coordinate plane. My parabola vertex would normally be at 0, 0, but now it's going to be shifted left 2 and open upward. Problem number 88 is the inverse of a function. It says find the inverse of f of x equals the square root of x minus 5. So the first thing I'm going to do is replace f of x with the y coordinate. So y equals the square root of x minus 5. Now to find an inverse of a function, I'm going to just swap the x and y, and then I'm going to resolve it for y. So instead of saying y equals the square root of x minus 5, I would have x equals the square root of y minus 5. And now I just have to go through the process of solving for this y. So first I'm going to undo the square root by squaring the right side. If I square the right side, I also have to square the left side to keep the equation in balance. So x squared is just expressed as x squared. And remember, the square root and the square undo one another, and so I get y minus 5. Now simply all I have to do is solve for y, which means I will add 5 to both sides. X squared plus 5, all I could do is express that as x squared plus 5. Negative 5 plus 5 is 0, or as some people say, it cancels out. 0 plus y is y. And so my inverse, which I will express using a little negative 1 on the function of x equals x squared plus 5. Problem number 89 is logarithmic and exponential forms. It says write in exponent form log base 2 of 16 equals 4. So when you listen to the log base 2 of 16 equals 4, you hear the word base with the 2. that's going to form the base of the exponential form. I'm going to take the base 2 and I'm going to raise it to the 4th power, and that will be equal to 16. And so the log form, log base 2 of 16 equals 4, in exponential form would be written 2 to the 4th equals 16. Problem number 90 is again logarithmic and exponential forms. This time it says to write in logarithmic form the exponential form 5 to the 3rd equals 125. So again I'm going to start with my base. I would have log base 5, and I'm going to follow the same process. Base 5 of 125 equals 3. So the exponential form, base 5 to the 3rd equals 125, would be log base 5 of 125 equals 3. Problem number 91 is the log properties. It says to write in expanded form log base 3 of x to the 4th over y to the 5th. So if you remember from the exponent rules, to divide exponents, we subtracted. And so we're going to do the same thing with logs. To write this in expanded form, we're going to write log base 3 of x to the 4th, and to show the division, we're going to subtract another log base 3 of y to the 5th. So in expanded form, it would say log base 3 of x to the 4th minus log base 3 of y to the 5th. Problem number 92 is again log properties. This time it says to write in condensed form 2 log base 5 of x plus log base 5 of 7. So I have two things happening in this problem. I have a 2 out front, and since this is multiplication, it's going to indicate that the x is being squared. So I would have log base 5 of x squared plus log base 5 of 7. The plus sign, or the adding of the two logs, indicates that the arguments are being multiplied, very similar to the exponent rules. So in condensed form, this would say log base 5, x squared times 7 is 7x squared. So I would have log base 5 of 7x squared. Problem number 93 is solving log equations. It says log base 2 of x plus 1 minus log base 2 of x minus 4 equals 3. So the first thing I'm going to have to do is condense the left side into a single log so that I can use my definition to set up an equation. So since this is subtraction, remember the two arguments are therefore being divided. So I would have log base 2 of x plus 1 over x minus 4 equals 3. Now that I have it condensed into a single log, I can apply the log definition. Base 2 raised to the 3rd power will equal the argument. So 2 raised to the 3rd power will equal x plus 1 over x minus 4. 2 to the 3rd is 8, so 8 equals x plus 1 over x minus 4. To help me out, if I want to put 8 over 1 so that I have my two fractions, I can then multiply both sides by x minus 4 to remove the denominator. So 8 times x minus 4 will be 8x minus 32. On the right side, x minus 4 divides out with x minus 4, leaving me with 1 times x plus 1. Now I have a basic equation. I'm going to subtract x from both sides. 8x minus 1x is 7x minus 32 equals x minus x is 0 plus 1 is 1. And here I'm back to a two-step. I'm going to add 32 to both sides. Negative 32 plus 32 is 0. 0 plus 7x is 7x equals 1 plus 32 is 33. And my last step would be to divide both sides by 7. So x would equal 33 over 7. Problem number 94 is solving log equations. It says log base 5 of x plus log base 5 of 4 equals 3 log base 5 of 2. So the first thing I'm going to have to do is condense the logs on the left side and condense the logs on the right side. Since this is addition of logs, my two arguments x and 4 are being multiplied. So the left side would condense to log base 5, x times 4 is 4x. On the right side, since I have a 3 out front and these are being multiplied, remember that indicates an exponent. So this would be log base 5 of 2 to the third. Now, since both of these say log base 5 equals log base 5, it indicates my argument 4x must be equal to the other argument 2 to the third. That's the only way those two could be equal. And so my equation would just say 4x equals 2 to the third is 8. Now I just have to divide both sides by 4. 4 divided by 4 is 1x, and I would find out that x equals 2. Problem number 95 is the change of base formula. It says log base 3 of 22. So the change of base formula says that I can change the base of the log by writing a ratio. So if I have log of a base a to n, that's equal to log whatever I would want to change the base to. I'm not going to write a base because that would indicate base 10 of n divided by log of a. Notice the base goes on the bottom and the argument goes on the top. So when I don't write a base, if I just write log, it indicates base 10, what's called common log. And so in my formula, log base 3 of 22, I can write with the common log. Common log 22 is going to go on the top part of the ratio. Common log, the base 3, will go on the bottom part of the ratio. And then I could simply punch that into a calculator. Common log 22 divided by common log of 3, if I round that off, is about 2.8136. Problem number 96 is systems of equations. It says 5x plus 3y equals 1 and 3x plus 4y equals negative 6. And we want to solve the system. So to solve the system, in this case, I'm going to use elimination. And I'm going to choose to eliminate the x terms by multiplying the top equation and the bottom equation by specific values. If I think about what would be a common denominator for 5 and 3, I would get 15. I need one of them to be positive and one of them to be negative in order to add to 0. So I'm going to choose to multiply both sides of the top equation by negative 3. Again, if I multiply both sides of the equation, I haven't changed the equality of the equation itself. The bottom equation I'm going to choose to multiply by a 5. So if I multiply the top equation by negative 3, it would give me negative 15x. Negative 3 times 3y is negative 9y. And negative 3 times 1 is negative 3. So I have the same equation, just with a multiple of negative 3. The bottom equation I'm going to multiply by 5. 5 times 3x is 15x. 5 times 4y is 20y. And 5 times negative 6 is negative 30. Now to do elimination, I can add those two together. And what happens because of the multiplication that I chose, negative 15x and positive 15x adds to 0. Negative 9y plus 20y would be 11y, and negative 3 minus 30 would be negative 33. Now I could just divide both sides by 11, and I find out that y equals negative 3. Since I now know that y equals negative 3, I can back substitute that into either one of these equations. I'm going to choose the top one. You could use the bottom one. I'm just going to use the top one. So now I can solve for x. 5x plus 3, y we just found to be negative 3, equals 1. 3 times negative 3 is negative 9. And now I just have a two-step. I'm going to add 9 to both sides, so 5x would equal 10. Going to divide both sides by 5, and I would find out that x equals 2. So the system would be solved, x equals 2 and y equals negative 3. So that's it, part 3 of the algebra review. Use the handout provided to practice along with us. Keep working hard. You're definitely going to be successful. And remember, as we say at MathDogs, you got this.